This video presents our LREC 2020 paper entitled Transformer versus LSTM Language Models trained on Uncertain ASR Hypotheses in Limited Data Scenarios. This work was conducted under the COMPRISE project funded by the European Union's Horizon 2020 research program. Domain-specific and application-specific ASR language models require significant amount of in-domain text data for training, and this typically consists of manually verified transcriptions of in-domain speech data collected from the target application. However, such domain-specific text and speech resources are scarce, especially in the early development stages of a new application, in privacy-critical applications, or for under-resourced languages. Hence, the focus of this work is on training language models from a limited amount of in-domain speech of around 25 to 50 hours. More specifically, we train neural language models on ASR decoded graphs like confusion networks and lattices, which carry more information than the ASR1 best hypothesis. There are previous works which have studied training of n-gram LMs from ASR decoded n-best lists and lattices, as well as adaptation of RNN LMs on one best hypothesis. More recently, RNN and transformer models for ASR decoded lattices and confusion networks have been proposed for machine translation and spoken language understanding tasks. However, the focus of these models is to encode the ASR decoded lattice or confusion network into an embedding which can be used for further classification or decoding tasks. In contrast, training of ASR LMs need to address the problem of multiple uncertain outputs at each step. A recent work addresses this issue for training LSTM LMs on ASR confusion networks using different methods. The current work extends these methods to transformer LMs. We are interested in evaluating whether the self-attention mechanism of transformers can exploit alternate hypotheses represented by ASR confusion networks and outperform LSTM LMs in limited data setups. We will first briefly present our methods to train LSTM LMs on ASR confusion networks. In the sampling-based training method, we sample one complete path by sampling one arc at a time based on the posterior probabilities in each confusion bin. Given the sampled path, the LSTM LM can be trained using the standard cross-entropy loss. In the KL divergence-based training method, we handle the multiple arc inputs from a confusion bin by computing the LSTM hidden state for each of the arcs, followed by a pooling operation. In order to handle the multiple output arcs at each step, we adopt a loss function which computes the KL divergence between the LSTM LM predictions and the confusion bin posteriors, as shown in equation 3. Note that the sampling-based method can be used as it is with transformer-based LMs. The KL divergence-based training method can exploit the self-attention mechanisms of transformer LMs as presented in the following. We propose a hierarchical scheme for training transformer LMs in which there are separate arc level and bin level transformer layers as shown in the figure. The confusion network is first collapsed into a long sequence. This input is fed to the arc level layers followed by a pooling operation. Note that we update the self-attention mechanism to take account of the confusion bin posteriors. The pooling layer is followed by the bin layer transformer layers. And finally, the output embedding layer and the KL divergence loss. Note that this hierarchical scheme is used only during training. There is no distinction between the arc level and the bin level layers during inference on normal text sequences. In order to evaluate the training of neural LMs on ASR confusion network, we use two different datasets. The first one comprises the English subset of the verb bubble corpus, and second one is the scenario-only subset of the AMI corpus. In order to simulate the limited data setups, the two datasets are split into 4 subsets as shown in the table. In addition to the VM and AMI in-domain datasets, we use transcriptions of the 300 hours of switchboard corpus as the out-of-domain data to pre-train the LMs in the adaptation setting. Some more details of our experiment setup are listed here. For the VM setup, we use seed ASR AM and LM trained on the VM label training set. For the AMI setup, we use the pre-trained Aspire ASR models. We performed a hyperparameter search for the best performing transformer and LSTM LMs. We now present the perplexities of the LSTM and transformer LMs trained in different settings. Note that the LMs are trained on the combination of the reference transcriptions of the labeled training set and transcriptions obtained on the unlabeled training set, which could be the ASR1 best transcription, denoted as 1B, or the ASR confusion network. As a top-line reference, we also present the performance of LMs trained on a combination of the reference transcriptions of both the labeled and the unlabeled training sets. We first present the perplexities of the LSTM LMs trained only on the in-domain data. We can observe that the sampling-based method achieves the lowest perplexities. The reduction in perplexity is statistically significant on the VM test sets, as indicated by the bold font. In the case of transformer LMs trained only on the in-domain data, the sampling-based method achieves the lowest perplexities. However, the transformer LM performs better than the LSTM LM only in case of the VM test set. This could be due to the fact that the VM dataset has longer speaker turns of average 20 words as compared to average 8 words for the AMI dataset. We would also like to highlight that the proposed hierarchical scheme for training transformer LMs on confusion networks with KL divergence loss performs better than a vanilla transformer on collapsed confusion networks. We now present the perplexities obtained in the adaptation setting, wherein the LMs are first pre-trained on the out-of-domain switchboard corpus, then adapted to the combination of the out-of-domain and in-domain data. As expected, the overall perplexities obtained in the adaptation setting are much lower. However, this comes at the cost of a large conversational speech corpus with manually verified text transcriptions, which may not be available for most languages. Comparison of different methods in the adaptation setting shows that the training of the ASR confusion networks leads to perplexities that are equivalent to those obtained by models trained on ASR 1 best hypothesis. However, the gap between the 1 best baseline and the top line remains unfilled. This calls for better methods for training neural LMs on ASR hypothesis. In order to further understand the perplexity reductions obtained by the different methods, we performed a qualitative analysis wherein we dissect the LM perplexities for words in different frequency groups. A plot of the perplexity obtained by the transformer LMs versus the frequency of occurrence of words in the in-domain training set is shown here. We can observe that training on ASR confusion networks, both using KL divergence and sampling-based methods, gives large perplexity reduction for the less frequent words. These reductions are smaller in the adaptation setting because the less frequent words would have been seen during the pre-training stage. Moving on to the conclusion, the main takeaway from this work are as follows. The sampling-based method leads to the lowest perplexity. The hierarchical scheme leads to better transformer LMs when training with the KL divergence loss. Overall, the transformer LMs perform better than the LSTM LMs on the AMI dataset, but not on the VM dataset. Neural LMs trained on ASR confusion networks are better at predicting less frequent words. However, there is a need for better methods to meet the expected perplexity and word error reductions.